fundamental to AI.
AI will generative AI.
In the world of AI,
AI के बारे में ज़्यादा सीख रहे हैं.
it is time for AI Decoded.
And thus, I got into AI. In the next 10 minutes, I will take you on my journey of learning AI, building a simple sentiment classifier to trying to wrangle a ChatGPT-like chatbot. It did sound cool to start learning AI, but 90% of the stuff that I did was data pre-processing. Because remember, garbage in, garbage out. I majorly explored NLP. It's short for natural language processing, basically teaching AI to understand human gibberish. And my first project was a sentiment classifier. Give it that was a great movie and it says positive. But if you go, that was a dog garbage movie, it screams negative. Yeah. It's kinda similar to Hot Dog Not Hot Dog app from Silicon Valley. But hey, it taught me a lot. Computers don't speak English, they speak in numbers. And first, I had to convert this English statement to numbers. But before doing that, I cleaned up the dataset a bit by removing unnecessary punctuations. Then I removed the stop words, the words like I, me, myself. For example, this statement is positive, and after removing stop words, it's still positive. Removing these unnecessary stuff which don't really add much value in determining the sentiment of the statement will help our model to learn from less but more trivial stuff. And then I simplified the words further by lemmatization, basically reducing the words to their root form. Example, this statement is negative, and after lemmatization, it's still negative, but minimal stuff for our model to learn from. Lemmatization, unlike stemming, does not directly remove the suffix of the words. Instead, it looks at the given text and checks how does it affect the context of the sentiment while reducing it to its root form. You can check the description for links on learning more about them. Finally, it was time to convert the statement into numbers. Two of the popular ways I learned were count vectorization, counts how many times a word appears in a statement and assigns a number accordingly. And other one was TDIDF. Basically, how important is the word in the dataset. Google the math, it's fancy. And finally, I trained my logistic regression model on my clean data. Logistic regression can be used for binary predictions such as classifying sentiments in our case. It's derived from linear regression which can be used to predict X based on Y. For example, predicting height of a person based on weight. I then split the data into training set and test set using this library and then just use the training set for training the model and test set to evaluate it. And done. My classifier was alive. It could now take in your text and say, well, positive or negative. But of course I didn't stop there. I learned a couple of more concepts such as naive Bayes, support vector machines, LDA, LSA, parts of speech tagging, and named entity recognition. One of the use cases for pause tagging and NER is to use them to check what kind of data or words appear most frequently in your dataset, mainly while analyzing it for further classification. For example, words like free, discount, etc. appears mostly in spammy emails, while classifying your emails as spam or not spam. And then I wanted to go big. Large language models. So I went to Hugging Face, it's like GitHub for AI, and explored LLAMA, Facebook's open source LLM. LLAMA has a model with 8 billion parameters and my laptop was not on the same page with me to run that. So I tried Google Colab with a T4 GPU, but even that struggled. Then I learned about pruning, PEFT, LoRa, and quantization. Fancy word for make the model smaller. LLMA comes in 8 billion and 70 billion parameters, so I used the 8 billion one and downgraded its precision to float 16 with QLoRa, short for quantized LoRa, and this saved a lot of memory and my sanity. It ran a bit slow, but it worked. Check out Bits and Bytes config in Hugging Face and quantized LoRa to know more about quantization. Then comes the dataset. I used a medical Q&A dataset from Hugging Face itself, tagged it with start and end special tokens, and a custom token to let the model know where the patient question ends and where the doc response begins, and fine-tune the model with that. LLMs, by the way, are just giant prediction machines. They predict the next word based on the previous words. This time, I didn't remove stop words or punctuations. Why? Because these models actually need all that stuff to make sense of the language. Training the model with all the 100k rows would actually be painful. So I just truncated the dataset from 100k rows to just 3010 iterations just to test it out. And the model sucked. But I understood how it worked. Then I learned more about overfitting when your model memorizes the data like a bad student, and underfitting when your model doesn't even try. Also, if you are curious, you can look into transformer architecture, which paved the path for this rapid AI advancements while traditional RNNs couldn't. And thus, the first 2 weeks ended with me at an Apple store in Delhi, charging my phone. Yeah. Then watched a group of Japanese performers doing Chaya Chaya, and finally flew back to Bangalore, wondering, is there a way to get these LLMs to give relevant answers without spending days fine-tuning the models? The next morning, I started learning about Retrieval Augmented Generation, RAG. RAG is useful for providing custom context or real-time data to a model. For example, imagine a dataset of medicines and their prescriptions. As this dataset grows, fine-tuning an AI model becomes costly and impractical. That's where RAG comes in. Instead of responding directly to a query, the model uses a tool to extract relevant symptoms, then feeds them into a retrieval system that looks up prescriptions for those symptoms. This provides the context the model needs to respond appropriately. Similarly, multimodal systems act the same way. First, the user query is processed to identify which model is best suited for performing that task, and it's just forwarded to that model. Okay, I found a patient Q&A dataset on Hugging Face and combined both the question and answer into a single text. Normally, it's better to provide smaller documents, but since the Q&A conversations were short, I chose to append them together. While I could have cleaned the data by removing greetings and other unnecessary statements, this dataset did not include much of those, so I just skipped it. However, I couldn't rely on simple query matching to retrieve those documents because it might not find relevant documents, plus we want this to be fast. Symptoms in different queries might be related but phrased differently. So I explored vector databases. Vector databases works with, well, vectors, basically multidimensional representation of data. To calculate similarity between these vectors, I used cosine similarity rather than dot product for better accuracy. You can know more about these stuff via the links in the description. To vectorize the Q&A dataset, I used another model named PyOBERT, an NLP framework with an encoder architecture that is fine-tuned for medical purpose. I then pushed the vectors to Pinecone, a cloud-hosted vector database solution. I also wanted my model to handle generic questions like who did the first heart transplant, which might not be in my Q&A dataset. For that, I added a Wikipedia wrapper tool. Both the vector store and Wikipedia tool were fed into LangChain's LangGraph agent, which selects and queries the appropriate tool. You can check about LangChain via the link in the description. I deployed this system on Cloud Run with 8 gigs of RAM and no GPU, which causes slow cold starts, but subsequent queries will be faster. Then created this basic UI and deployed this one in Vercel. Just like that, my app was ready. That's it for this video. See you soon. Go ahead and smash and kick that subscribe and like button.